before doing a couple examples, I want to just go over a few things. The 2-sample t-test is less sensitive to not meeting conditions than the 1-sample t-procedure. So if I don't have completely normal distributions, I'm going to be okay. And if you look at the second thing, it says if sample sizes are equal and populations have the similar shapes, okay, so they look somewhat the same, our p-value is going to actually be quite accurate even if we have small samples. Okay, however, if our populations have different shapes, meaning one's maybe skewed right and one's skewed left, then we would need to have larger samples of the same size. Having samples of the same size is actually going to be a good thing. So we also need to follow the rules of the sample size needed for the 1-sample t procedure, but we use the sum of the 2 samples. So in this case, I'm always going to be looking at like N1 plus N2. Remember, our rules were like less than 15. We really needed to have a normal distribution. If it was 15 to, this is where it's kind of subjective, 30 or to 40, we just want to make sure that it's not heavily skewed. And then if we have distributions that are pretty skewed or have outliers, we want our sample, the sum of these two, to be more than 40. And remember, in some cases they say 30. Okay. Our option 2 for degrees of freedom is going to be the more conservative one. Remember, that's where you take the N1 minus 1 or the N2 minus 1, whichever is smaller. Okay, and that's going to just give you the larger t that we're going to have to use. Okay, once again, we're dealing with some pretty wordy examples, but they're trying to give you all of the information that you need so that you can go and do a proper test here. So I'm going to let you pause the video and read the information to yourself, and then we can continue on with going through. I've done most of the work for you as far as putting up the stem and leaf plots, a box and whisker plot, finding the means and standard deviations of my samples, so that we don't have to spend a lot of time doing the number crunching. Okay, so let's go over what information I actually have here. So if you look at the table, I'm going to let treatment be 1 and control group be 2. And I'm going to be consistent with that. So our treatment group is going to be, like, we're going to have our N1 and our N2 and our X bar 1 and our X bar 2, our S1 and our S2. And I'm going to be consistent, and treatment will always be 1 and control will always be 2. So when you look at this like 291, what does that actually mean? It means that that subject, that one person, increased their speed by 291 seconds after the treatment. Okay, so you'll notice that some of them have negatives, meaning that they had the treatment, but then when they did the test after the treatment, they actually were slower. Okay, in the treatment group, you'll notice that there's 3 negatives, but there's quite a few high numbers, and in the control group there are, it looks like 3 negatives as well, but not as many high numbers, meaning that you didn't have as many people improve as much. When we look at the stem and leaf plots, you can see that this one right here looks like it could be skewed a little right. This one may be skewed a little right as well, but neither one of them has huge outliers, and they're not completely the same. But one thing that I do have here is my sample sizes are both 21, which is going to be nice. And when I add up my 2 sample sizes, I get 42, and that's going to meet the condition of having at least 40. Okay. I also have my sample means here, so I have my 132.7 and 59.67 for my control group, and my standard deviation is 98.44 and 63.04. Okay, now instead of using the formulas on this one, we are going to use our calculator, but before I start, I need to state my null and my alternative. So my null is what we assume to be true. So in this case, I'm going to assume that the difference in their time should be equal, right? The treatment doesn't help, so we assume that if whether they had the treatment or not, they're still going to improve or not improve at the same rate. Okay. my alternative is I would hope that having some sort of treatment would improve their time. So I'm going to test to see if that treatment actually worked to help speed up the time for this laparoscopic test. Okay. So I'm going to go to my calculator, and on my calculator you'll notice that we have all those tests, stat tests, and this time we're going to do number 4, which is our 2 sample t test. On your calculator you'll notice that it'll ask for all of the information that I put up here at the top. Now it does state for the x1 first, x bar 1, s1, and then you put in the n1. Then you'll have x2, s2 sub 2, and then the n sub 2. And then once you do that, it's going to ask for the less than. So we want greater than, so make sure that in this case you're going to do the mu1 is greater than mu2, because that's the way we set it up. And then it's going to ask about pooled. We are always going to say no on the pooled. We are not going to do a pooled t-test. So take a few moments now to pause this and put this information into your calculator on the stat test number 4 and see what you come up with. So I came up with my t equaling 2.86 and my p-value of 0.0036 if I round that off. And you'll notice that you have this degrees of freedom of 34.04 because, like I said, the calculator uses a different formula for degrees of freedom, and I'm fine with using that degrees of freedom. So let's just quickly sketch this so we have an idea of what we're looking at. Our null is that the difference is 0, so that's going to be my mean in my sampling distribution. My t I came up with was 2.86. Now remember, your t distribution is a little bit thicker at the end, so it may not be quite as far over as if I had a z, but my p-value is still 0.0036, which is quite small. So if you looked at this problem, it asked, does the Nintendo Wii training significantly increase the mean improvement time? So I need to decide, does it significantly increase the mean improvement time? My p-value is pretty small. Would my p-value be smaller than any sort of alpha that I would possibly give you on this one? Because remember, our alphas are either 0.1, 0.05, or 0.01. So in this case, we would reject the null. And when we say that we reject the null, we would basically say that there's strong evidence to say that the Wii training significantly increases the mean improvement time